So, welcome here once again to the lecture 8 of this series. So, today we will learn about first we will learn about Duffing oscillator system. Duffing oscillator. So, what is a Duffing oscillator? So, basically, it is a kind of oscillator which is nonlinear term. So, we know a simple harmonic oscillator whose equation looks like this: s square x. And if there is any driving term, so there is f drive. Now, if there is damping, so there will be here the damping will be gamma x dot. So this is our equation for a damped harmonic oscillator. Now, if you have a Duffing oscillator, so in that case, the equation becomes x double dot plus omega square x, which omega is a natural frequency. Then we have this damping term, and after that, we will have an x cube term, and there can be a drive, and so on. So here this equation, so this is the Duffing oscillator equation. So why this is important? So because here basically you have this beta term, and beta term is and you can see it is x cube. So this is a nonlinear term which is being added to the equation. So that is why it is a nonlinear oscillator equation. Okay, so you may think, why do you care about? Why should I care about this Duffing oscillator equation, this simple harmonic oscillator equation? So let me motivate you. So if you have any kind of potential, so for example, this is your x-axis, and this is your potential axis, and you have some kind of potential. So suppose it looks like this. So this is not harmonic oscillator potential. So how would a harmonic oscillator potential will look like? So for harmonic oscillator, we know potential is basically half kx square. So if you plot it with x, so basically it will be at x equal to 0, your potential should be 0, and it will be like x square time outcome. So this should be your potential. So, okay, so this is our harmonic oscillator potential. So now, if you have any general kind of potential, so it can be of this kind, it can be of, it can be of different kind of potential. So whatever the potential form is, so whenever you have a local minima, so for example, suppose you focus, you now focus on this region. So if you have a local minima, you can expand your potential around the local minima like a harmonic oscillator. So this, if your system is trapped here, and if it performs of and if it performs motion with small amplitude, so in that case, any arbitrary potential around a local minima, that can be treated as a harmonic oscillator potential. So let me write down it first. So any arbitrary potential when treated around a local minima and the system performs motion with small amplitude, around the local minima, that can be treated as a harmonic oscillator potential. So let me show you how we can do that. So I mean, suppose you have your this is your general form of potential, and suppose x equal to x0 is a local minima. Now how we can write this? So we know from Taylor series expansion. So Taylor series expansion, that if we want to expand a function around position. So for example, suppose we want to expand this around x equal to x0. So this will be f of x0 plus x minus x0 del f del x at x equal to x0. Then we will have x minus x0 squared divided by 2 factorial del 2f del x square. Here we have x equal to x0 plus x minus x0 cube by 3 factorial del 2a del 3a del x cube x equal to x0, and in this way it will go on. So if we assume our function to be perfectly differentiable, so I mean analytic, so it will be differentiable for all orders, and so then if this is a minima point, then this should vanish. So df dx at x equal to x0 should be 0 if x0 is a minimum. So that is why if you expand this ux around x equal to x0, which is a local minima, then you will get this term del u del x at x equal to x0 should vanish. So this will be your this term will give 0, and there will be another term, so which is so the third term. So I mean now if you so what is your ux will look like now? So this is ux0 plus x minus x0 squared by 2 factorial del 2u del x squared at x equal to x0, and there will be order of x cube. So now if we assume that the x is very small, so x minus x0 is very small, so that this x minus x0 square it is larger than x minus x0 cube, so you can neglect the higher order terms. And once we can neglect the higher order terms, then you can write down this ux to be ux0 plus so 1 by 2 factorial del 2u del x square at x equal to x0 multiply with x minus x0 square. So we are neglecting the higher order terms, and since this is a constant value, so I mean potential at x equal to 0, so we can treat it to be 0. So consider, so let us consider it to be 0. So if I consider it 0, then we will have our ux like this. So half, and we can, so let us call this k, because we are evaluating the second order derivative at x equal to x0, so it will give us a number. So that number we are calling it as k, and also suppose x0 is 0. So this is a reference point, so we can change. So this x0 we can assume it to be 0. I mean we can assume it to be the origin about so if we assume it to be origin, then it will be 0. Then what will be the ux look like? So it is basically half kx square. So as you can see, so this is the potential of a harmonic oscillator. So from that, if you want to calculate the force, so force is basically du dx. So this x is the displacement from the origin. So origin is 0, so that is why it is, I mean this is the displacement from origin. And here what you can write, so this will be minus kx. So if we write it in our equation of motion, then we will get mx double dot equal to force, so which is basically minus kx. So we will left with mx double dot plus kx equal to 0. So from that we can write x double dot plus omega square x equal to 0, where omega is this root under k by m. So now you can see that in that way, so we have, so this is the classical harmonic oscillator equation. So I mean we haven't, so here what we have done, we haven't assumed any general we haven't assumed any particular potential. So we are considering any kind of general potential, and we suppose we want to I mean look at the behavior of the system. So if the system is trapped around the local minima and if it performs motion, then around that minima, if it have very small amplitude of motion, then its motion can be treated as a harmonic oscillator. So we can treat this system as a harmonic oscillator, and we can apply the methods that we generally use to harmonic oscillator system. So that is why it is very important to learn harmonic oscillator system. But if the amplitude of, I mean, if the amplitude of motion that is very large, so in that case, it will no longer be a harmonic oscillator. So because in that case, you will have this higher order terms also. So that is why, I mean, so that is the origin of this. We can see that it is a harmonic oscillator system if the amplitude is small. But now, what will happen if the amplitude is large? So when the amplitude of motion, so when this amplitude of motion is larger, so when this performing motion is large amplitude, so in that case, this x minus x0 cube and higher order terms, so they cannot be neglected. So suppose you have been included the third order term, then how will your potential look like? So this term will be still zero because this is the condition. So if it is minima, local minima, then it will be zero. So ux is basically we have ux0, then half kx square. Then suppose there is the next term which will be 1 by 3 factorial. So this will be like so let us call it k2. So k2 x cube, and in that manner, so let us call it k3. So k, then we will have k4, 3 cube 4 factorial, and here we will have x4. So in that way, your potential will progress. And if you want to calculate force, so force is basically minus du dx. So here you will have term compared to x, so minus sign minus kx. Then we will have let us call it minus zeta x square. Then we will have term minus beta x cube, and in this way you can proceed. So I mean you can see that for any potential, so I mean, so this damping oscillator equation or the simple harmonic oscillator equation, that doesn't, I mean, that is not limited to any I mean oscillator kind of system. So this can be extended to any kind of system, because for any potential you can, for any kind of potential you will always have some local minima, and around that local minima, if your system is performing small amplitude motion, so that you, so then you can treat it as a harmonic oscillator system. And if your system is performing oscillation with larger amplitude, then in that way, then there you have to, I mean, include the higher order term. So in that case, inherently in your system, nonlinearity will come into play. So in the, so that is why it is important to learn about the simple harmonic oscillator system, and I mean a system where nonlinearity comes in inherently. So let us try to look at how the potential will look like. So let us try to plot some potential in MATLAB. Okay, so let us first plot the harmonic oscillator potential. So we will have to have some k value. So let us consider it to be 10, 1 for now. Then we will have x, because our potential basically is of this form. So I mean half kx square. So this is the potential from form. So you want to look at the behavior of it, how it is changing. So let us try to do that. So let me write down potential. So since these are simple harmonics, so potential simple harmonic, and here what we have. So basically we have half, then that will be multiplied with k, and that will be multiplied with x square. So this is your potential. So and I mean if you run it, so it will give error because you haven't defined x yet. So you have to define your x array. So let us take it from minus 10 to 10 in steps of maybe zero point 0.2. So let me run it. So this is potential plot. Okay, so here I mean what you have to do, obviously you have to do the matrix, I mean elementary operation. So here you can see that this is a potential array, and this is our x array. So what you can do, we can simply plot them to visualize it. So plot x potential simple array. Okay, so this is how our potential plot will look like. So you can see that this is a local minima. So around this local minima, I mean, so I mean, if we have any kind of general potential, so let us try to have some kind of different kind of potential. So potential. So what should be the what can be the potential? So I mean, let us consider to be sine x. Then you maybe you will have e to the power of minus x. Then we will have maybe minus x cubed. So suppose we want to visualize both. So here we have to write down the whole down. Then plot the other potential also. So x potential other. So let me run it. Okay, so you can. Okay, so since the scales are different, so you can try to, I mean, uh, plot them in log axis. So and also make it smaller. Okay, so this is our harmonic oscillator potential. So which is minima around 0, and this is the potential which we are, I mean, so we can make it to be smaller. Yeah, so this is harmonic oscillator potential, and this is the other potential which we have considered. So I mean, so here as you can see, so so this is for example a local minima, and you can try to expand it more to look at the behavior. So there is no, so maybe x minus 3. Let me return to the original one. Because at least it has one local minima. So I mean your function can have all one local minima or multiple local minima. So let me increase the limit to check if there is any other local minimum. Okay, so not. So maybe uh, some kind of, I mean, x plus 3, and we can increase still not. So maybe 5. Okay, so this can have some. Okay, so let me go to the previous one. So yeah, go up to 4. Yeah, so for example, in the potential which you are plotting, so this one is a local. So around here we have a local minima. So I mean here we will have a minima point, and around the minima point. So if our system is oscillating around this value, then it for this small range, we can consider the motion of the particle to be harmonic oscillator. And if it performs, I mean, with slightly larger, so that I mean we have to take into account the higher term. So in that case, in that case we have to consider the higher order terms like x square x cube. So in that case, we can treat it as a Duffing oscillator system. So that is why, so that is the motivation behind learning this oscillator kind of system. So I mean you can, I mean these are applicable to any kind of system. So so any physical phenomena, any system we are working on, so that for small amplitude around local minima is a harmonic oscillator, and if it amplitude is slightly larger, so that I mean you cannot explain with it harmonic oscillator, then uh, you can consider this as a Duffing oscillator system, and you can try to explain the system with the equation with this, I mean nonlinear types of equation. So it is important to learn about the system. So you can plot, I mean Duffing potential also. So let me include the higher order terms, potential higher. So this will be our lowest order, which is this one, plus we will let us have 1 by 6. Okay, so let me just consider it to be another constant. So just kx square k2, that will be multiplied with x cube, then we will have k4, and that will be multiplied with x to the power 4. So now we can also plot this potential in the same graph. So we can hold on again, and we can plot this x potential high. Now, I mean, if you run this, so it will give you error because we haven't defined this k4, k3, and k1x yet. So k1x is basically half k, so which is basically 0.5. Then we have k2, so let us consider 1. We have k3, let us consider 2 for now, and let us look at the potential. K3. Okay, so and in this case here we can have the log scale around y-axis. So we can just reduce it and we can set the y-axis to log scale, so which you have learned in the previous day. So set GCA scale log. This this. Okay, so and we know that in log scale, so negative values are ignored. So you can, so whenever the system the potential has negative value, so that is being ignored here because so you are taking the y scale to be log. But I mean this is a good way to visualize. You can, for now you can just comment it, and I mean this is your system. So this is your harmonic oscillator potential, how is it is look like. So this is the, I mean, other potential which you have considered, and this is the potential which this is the higher, I mean, potential up to order 4. So this is how a potential look like. So just let us look at the last one and try to look at the output. So let me try to change the parameter and look for something interesting if it happens here. Okay, so this is how, I mean, you can plot the potential. So and this is, I mean, the basic way of understanding how nonlinearity can arise, I mean, in any kind of system. So now so consider a specific case where nonlinearity can arise. So for example, suppose you have this kind of system where you have a, so for example this is a capacitive arrangement. So yeah, in capacitive arrangement, and you are, I mean, so this is a capacitive arrangement, you are applying some voltage across these two junction. So if you are applying some voltage, then we know that the electrostatic potential is half CV square. So now, suppose in this in this arm of capacitance, instead of so for example, this is, I mean, suppose this is a conducting plate, and suppose here instead of conduct, so I mean, suppose instead of conducting plate we have a membrane. So I mean this can be as a 2D membrane, or we can have string also. So what will be, so what will happen if we apply some voltage across this? So if we are applying some voltage, so it will create a force on the string in this direction. So the, so due to the appliance of the force is due to the appliance of the voltage, its equilibrium position will change. So if we don't apply some voltage, suppose this is its original equilibrium position. So it will have a certain so I mean so it will have some elasticity, and it will have some pulling force, and depending on the interplay between this, it will have some certain equilibrium position. So from, so this is the equilibrium displacement. Now suppose if you are increasing the voltage, so in that case the equilibrium position will change. So maybe for larger voltage, the equilibrium position will something look like this. So from the, I mean, from this axis, so if you consider this to be your origin, so this will be now the displacement. So with increasing gate voltage, which is V, so equilibrium position of the string will change. So with changing v, so we will have x. I mean this equilibrium position will change. So now how can we write this capacitance? So it is basically, we know that if this is per uh, if this is permeability, permittivity, then we can write as epsilon naught A by D. So where D is what? D is the separation between this between the two arms of the capacitor. So D is separation. So now this D is a function of voltage. So as we are applying voltage, so D will change. So D will change with increasing gate voltage. So now if X is the separation, so if we consider, so if we consider this separation to be X, then what will be the D for, I mean for a particular gate voltage? So this D we will have to replace with D minus X, because D is the total separation which is fixed. So this is, I mean this is the D, this one is D, but I mean we are having I mean this membrane is also deflected by amount X also. So with increasing voltage, so the separation will be D minus X. So let me draw it clearly here. So this is one arm where we have this membrane, and this is the other arm. So separation between these two membrane is D, which is fixed, and if this displacement is X, then this is D minus X. So now if I write down what is the capacitance, then the capacitance will be like this: epsilon naught A by D minus X. So what will be the what is the, I mean energy stored? So energy stored in the capacitor, a potential energy that you can write as half CV square. So this is basically epsilon naught A V square by D minus X. So now we can expand this, so by D, and this will be 1 minus X by D to the power minus 1. So this is the potential energy stored in the capacitor. So from this potential energy stored, I mean we can expand this term. So 1 minus X by T to the power minus 1. So we can, so it will be 1, and then it will be a function of X. Then I mean we will have some term plus X squared, then X cube, and in this way it will go on. So here you can see that in the case of this membrane also, so I mean if it is deflected from its original position, so I mean if we put a membrane in a capacitive arrangement and if we apply some voltage across it, so there will be, so due to the, I mean due to the deflection of the membrane from its equilibrium position, so there will be a nonlinear term will emerge in the energy equation. So and also, I mean, so with larger so I mean deflection, so there will be some inbuilt electrostatic energy. So electrostatic energy, so that is basically a function, I mean of x squared, and will a function of x to the power 4. So electrostatic energy is also a function of x to the power 4. So there are two sources of nonlinearity in this kinds of system. So two, I mean, these are two major sources. So there can be other sources also, but so one is what? First one is electrostatic energy. So let us. So first is electrostatic, which is, I mean which is coming due to the expansion term. So it can have, I mean, x term, then x squared, then x cube, and so on. It can go on like this. Then we have this elastic energy. So here we have, I mean, we can have x squared term, some constant plus some constant x to the power 4 term, and I mean from bending digit and so on. I mean, so it comes, these terms come from the theory of elasticity. You can check that, but the main thing is that, I mean, so there is two contribution of nonlinearity. So now if you write down the equation of, I mean, motion, then in that case you will have this x double dot term, then you have this omega square x term, and after that you will have term which will be maybe proportional to x squared, then x cube, and there can be derived term and so on. So the idea is that if for this kind of system we I mean, so if we and if we apply some voltage to it, so there the nonlinear terms, nonlinearity will come. So and this nonlinear term can arise from two phenomena. One is the elastic energy stored in this kind of membrane, and another is the electrostatic energy stored. And so, I mean, so this kind of system is widely used in NAMES research. So, what is this NAMES? So, this is basically nano electromechanical presenter system. So, for example, I mean, so what so basically, I mean, this membrane can be, so generally people do research with graphene membrane, with, I mean, silicon nitride membrane, and with other membranes of other materials also. And I mean, so and also we know that graphene has some inbuilt nonlinearity, so that is why when you are dealing with this kind of system, so I mean, it is important to consider those nonlinear terms. So with that, so let me write down formally the Duffing oscillator equation, which is x double dot plus gamma x dot plus omega square x and beta x cube to f dot. So this term is called the Duffing coefficient, and so it can be greater than 0 and it can be less than 0. So this, when it is greater than 0, so it is known as hardening case, and this is known as softening case. And so I mean, you maybe so you will encounter with this tapping oscillator system and a more complex kind of oscillator system in nonlinear dynamics. But here I will, I mean, I will just, I have just introduced you to the basic concept of how you can, for any kind of system, this damping kind of oscillator system can emerge. So it is important to understand about the system. And so now we will try to simulate this kind of system in MATLAB and try to explore this. So let me go to MATLAB. Okay, so write down the equation. So I have to define the parameters. So let me here define the equation which I will use. So that will be m x. So let me write it here. So that will be that will be easy to understand. So the equation we are using here is m x double dot plus gamma x dot plus beta by m x cube. Then we have omega square x, and we will have, I mean, so and that will be, and there will be some drive. So let me write the drive here. So f drive, or we will call it, we can call it epsilon. So epsilon divided by m, and will be cos omega ft. So this is the equation which we will use. So this is the, I mean, Duffing nonlinearity. This is our standard. This is our natural frequency. This is the damping term, and this is the driving term. So let me write down the. Let me show you how to simulate this. So let us consider m to be 1. Then we have, I mean, natural frequency called, let me call it omega. So 2 pi 1. Then we will have the gamma. Let me define it as also 2 pi, maybe zero point 0.2. Then we have the beta, which is, let us take it to be 5. Okay, for now let us take to be 5. So this is the parameter of the system. So system parameters. Then we will have drive parameters. Then what are the drive parameters? So let us call omega f, which is let us take it to be omega now, so because we are driving at the natural frequency. And then we have, so maybe drive strength. So for now, I mean, we can, so I mean, previous day we have show you how you can simulate the system for one drive system. So here, I mean, we will simulate for increasing number of drive states. So I mean, we'll look at the response for a range of drive states. So if you want to do this, if you want to do that, then what you have to do, you have to define an array. So let me uh, write down the array like this. So it will start from 0, and the step size maybe zero point 0.1, and it will go up to 1. So this is my drive strength. And so let me write down the function. So so now what are the variables in your function will be? So in your function, I mean, this we have defined. So if I want to write down this equation, this t will be a variable, x will be a variable, and this epsilon will also be a variable, which will, I mean, which will be selected from this drive strength array. So for now, we have to write here t, and t is a variable, and suppose we are writing, I mean, x. So this is second order equation. So we will recompose it into first order. So let us call that array to be y. So this will be t y. After that we will have, so epsilon also is a variable. Now here we will write the function. So since this is a second order equation, so we will have two. So let us create two array. I mean one array with two row. So first row, so dxdt. So what dxdt gives? It basically gives v. So if we want to store it in second element, then in second row, then we have to write y2. So this y is our, I mean, phase space vector. So y, all the elements along first row, so they have the uh, displacement value, and along the second row they have the velocity value. So the first function will be this, then we will have the gamma, then it will be multiplied with y2, because in the equation we have gamma v, then we will have here minus beta, which is our nonlinear term, that will be divided by m, and here it will be multiplied with, so beta x cube. So what is x? So x is our y1. So you have to write here y1, and that will be dot star cubed, and you can, I mean, that is not so, and then we will have minus omega square. So omega square, and then we will have y1, because there is omega square x in the given equation. Then we have the drive term. So and here, so how the drive term will look like? So here we will have minus epsilon by m, so star cosine omega f. So this is the drive. This is the drive frequency. So omega f multiplied with t. So this is the functional form of our equation. So here this is the function, and then we have to store the initial condition. So let me store this in y0. Let me create another variable which is y0, and it is, so this is the initial position. Then we have initial velocity, and let me define what is the, so t0 is starting time. So let us take it to be 0. Then we have t to be final time. So I mean, we are simulating a system with frequency 1. So it has natural frequency 1 hertz. So if you want to look at the steady state response, so I mean, you want to go up to, I mean, you want to simulate at least up 100 oscillations. So let me take t to be 300. So 300 oscillations, 300 cycles it will perform. So for the simulation time, so I mean, so it will reach, so we are hoping that it will reach its steady state. So we will check that if it is not, if this time is okay or not, but for now let us take this time to be 300. Then take, I mean, let us consider the number of points that will be there in the time array. So let us consider to be 1 multiplied with 10 to the power 4. So this is our n. Now what you have to do, so since we will run an array for drive strength, so for each drive strength you have to store, I mean, if you want to okay, so storing part let me do it later. So for now let me just let me show you how you can solve this. So how will go, so first we will run a loop on drive strength. So for I equal to 1 to length of drive strength, and here what you will do, so I mean, so we have to pass this epsilon to f. So this drive strength will store in epsilon here. So epsilon will be equal to drive strength, and there will be, so here we will have I. So ith element of the drive strength that is being stored in epsilon. Now, I mean, here what we will do, so we will write down a function. So we know how to write down local function. So and that function will calculate. I mean, what? Let me name the function as rk4, and so since you are so what it will give you the output, and so here basically I'm calling the function. So I mean we will write it later, but for now let me think of what the function should take as input. So it should take I mean the function, so this if we have to give this as an input here, then we have to give what is our time, initial time and final time. So initial time is t0 and our final time is capital T. So we are giving also this as an input. Then we will give what is our initial displacement and velocity. So let me write it here. So in the function we are giving this equation. Then we are giving this time range. We are also giving what is this initial position and velocity. Then n also is also needed. Then epsilon you have also to specify, and what it should give me output. So in the output what I want to store, so I want to have the y array. So okay, so let me call it ts. So this will give me the time array, and so let us have ys which will give me the so in the ys along. So first row, so I mean it will give me position and velocity. Then I mean we want to get the frequency array also. So I mean we can in the last we have learned about the FFT, so frequency, and also the absolute value of the I mean the uh, absolute value of the signal in the frequency domain. So these are the things which you want to get as an output. And okay, so for now this seems to be enough, so let us proceed. So this is I mean here we are calling the function. So after that what will happen? So now suppose you want to store what is this p1 value for different types. So how you can do that? So I mean you can create an array here. So td array, let us call it this like this. So what should be okay, so let me write it down later. So storing part for now, let's comment it out. Okay, and now suppose you want to plot what is the response. So figure 1, we want to plot frequency with p1. And I mean if you want to plot for multiple, so I mean this will plot for different types things. So we basically want it to be hold on and the end here. So this is your I mean here your system will calculate. So now we have to define what is this rk4 function. So let me try to write down the function. So whenever you want to define a function, so how you need to define it. So you have to write down what is the, so you have to tell MATLAB that this is a function. Then I mean what are the output that you want from the function, and this is the input you want to put it here. So let me just copy paste it. So in the function, this is the function name. These are the things which you will give as an input, and this is the values which the function will give as output. So so t0 t, okay, fine. Then so here so we can calculate what is dt here. So dt is basically nothing but t. minus t0 divided by n. So this is your dt. There you can write step size. Okay, so let us suppose you want to take this as output also. I mean, you want to look at what is the dt value, because if you don't take as a output, so MATLAB will not give you. I mean, so its value will not be stored in the workspace. So I mean, so the values that are being calculated inside the function, if you are don't passing it as output, so it will not be stored. So I mean, when you want to I mean work and I mean, so there can be cases where you don't want to store too much information, so you want to, I mean, your computation speed is your priority, and I mean you have to be concerned about the length also, about the RAM uh, also. So then you, I mean, in that case you can write down. It is always good to write down functions, because that generally does not store any values. Okay, so this is our test step size. Then what we can do, so we can define an array. So ts will be basically our time output. So let me create a ts array of zeros. So let us let the rows to be n plus 1. So there are n number of data point. So it will be n plus 1 1, and then let us take ys to be zeros, n plus 1, and then you will have length of y0. So I mean, why I'm writing a length of y0, because so since there is a there exists only one second order differential equation, so y0 length is 2. Now suppose you are working with two coupled equations, two second order coupled, which you have done yesterday in case of projectile motion. So in that case, you need four, I mean, initial condition. So that is why I mean I am writing here this length of y0 to generalize it. So this will give you the ys array, and then in t. So the initially you want to store what is t0, so that will be stored in t, and in y initially y0 will be stored. So this y0, which is the initial value, that will be stored in y, and the t0, which is the initial value of time, that will be stored in t. And with these values we will perform we will do the calculation. So and also we will have ts. So ts is the output array. So the first element of this ts output array, that should be your t. So in t you are storing t0, and that value you are storing in the first element. And similarly along ys, so first row and all column, so that should have I mean, so you have to have y transpose. Okay, now we will write down the main the core part of this rk4. So here you have to run a loop for I equal to 1 to n k1. So k1 is basically dt multiplied with function, and here you will have t, y, and epsilon. Then you will calculate k2, which will be dt, and this t will be now t plus 0.5 dot star. So here we will have dt. Then here we will have y plus 0.5 dot star. So here we will have k1, and the epsilon will be here. So this will be k2, and this will be k3, Here we will have basically, here we will have K2, and this will be K3, this will be 1, and this will be K4. So in this way, you have we have calculated all the four terms. Now what we can do? So basically, we can just update our y, so which is the initial value. So because y0 was stored in y, so initially y is y0. So these are initial, and with that value, the y value now will be updated. So y plus, here we will have this k1 plus 2 k2 plus 2 k3 plus k4, which will be, this will be divided by 6, and then we will have t equal to t plus dt. So here we are updating the time, and we are updating the phase space vector. And what will be your ts? So then after that, you have to, this ts, you will update here. So ts I plus 1 will be your t. And similarly, y is I plus 1, and here along all the columns you will store the y value. So here you will have y transpose end. So you have to end the RK for loop. So here you are calculating the RK for, and you are giving the time array and the phase space vector array as output. So then uh, also we want this function to return as the frequency and the uh, P1 array also. So how we will define the frequency? So defining frequency axis. So here we will have if s, for example, which is 1 by dt. Suppose you want to get this a phase also as, I mean, output. So this is the a phase, and then what should be L? So it is, as we have learned yesterday. So it will be length of ts minus 1, and then we will have the frequency axis, which will write down like this. So fs multiplied with 0 to L by 2, and this will be L, and here we will have L again. So this will give me the frequency axis. Now we have to calculate what is the P1. So for calculating P1, we are calculating the power spectral density. So how will get it? So let us call it FFT Y. So now, we want to calculate, we want to compute what is the FFT of Y1. So we want to compute the FFT of position or displacement. So we have to write down FFT, and here we will have Y is, so row all column 1. So this will give us the FFT value of displacement only. Then we will calculate what is P2, which is absolute of this one. So absolute of FFT Y1, which you have calculated, divided by L. Then we will have P1, which will be P2, and it will go from 1 to L by 2 plus 1. And since we want the energy to be conserved, okay, so this is L by 2. And since we want the energy to be conserved, so we have to multiply this with 2. So P1, P2, and minus 1, P2, and minus 1. So we can end it here. So in that way, we'll get the what is the PSD or power spectral density. I mean the information. So this is the Fourier transform value of the dependent parameter, and this is the frequency axis we are getting, and we are getting t and y as an output. And this is the function. So for function and this, okay. So this end is for the function. Yeah. Line 40. Mhm. That's what is the error? T0, T0, T. So yes. So function if let me call it to be T y0 in epsilon. So here maybe so that was the issue, I guess. So let me just type it and T1, then T0 equal to T1, and we have here T, which is TV2. Let me run it now. So now it is working. So the issue was that, I mean, so whenever you are defining a function, you cannot. So initially it was written like this. So I mean, whenever you are defining a function and you are giving input, so in that case you cannot. So I mean, you have to put all of them as scalars. So I mean, you cannot just write down this here. So I mean, this you cannot put any array in input here. So I mean, so I mean this TV, so you have to write down single value, I mean single variable. So TV, it can be I mean it can be a scalar or it can be an array also. So I am so this TV, so when you're defining this way, so I mean you're telling the MATLAB that this TV is an array and its first element, so store it in T0, and in the second the element of TV store it in T, but you cannot write down like this. So T0 TV, so you cannot write down in this way because I mean when inside this inside this first bracket you cannot put this third bracket. So I mean you can just simply put this as T0 TV, or you can call it as I mean TV. So and here when you're calling the function, you're telling that so there are two elements in this TV. So here, while calling it, you can use it, but when you're defining it, you cannot use this. So okay, function is fine. So let me run it. Okay, so it is giving me response around. So what is this value? So this is 1. Okay, so our system was okay. So type frequency was 1. So now just let me make this plot. So x lim, let me change the x limit. So maybe from 0 to 5, and also maybe the y scale to be log. So now let me run it. Yes, so you can see that this is how the system. Okay, so now just let me the system non-linear. So beta, let me make it 0, and let me see what is the response. So fine. Okay, so this is how the system will respond. Now you want to know if the time that you are using, so that is good enough. So I mean, what do you know? So if we have a harmonic oscillator system, and if we look at its phase space, then in the phase space, I mean, it should have a circular kind of thing. So how can you verify? So I mean, if you have a, for example, simple harmonic oscillator, then its energy we can write is half kx square plus half m omega square v square. So if x and v are two, if x and v are two, axes, then the total energy. So I mean, it will have a circular kind of behavior if the system has gone into steady state. So let me look at x and v. So what is how we can look at it? So basically this y is, so it has information. So this is our displacement and this is our velocity. So we can just simply plot uh, the first column with second column. So let me do that. So here we are doing the phase space plot. So what we will plot? So basically we will plot our y is all row first column, and y is all row second column, and maybe hold on. So let me check for a single type still. So for now, let me take this to be 1, and let me run it. Okay, so you can see that. So it is not. I mean, so let me try to make the damping to be 0 also. Okay, so you can see that it is not showing the circular. So what you can do? So we can try to change. So we are plotting from initial. So let me make it from, I mean, for example, so there are 10,000 data points in YS. So let me check from 1000 to end. And let me also put here the data points from 1000 to end. Okay, good enough. So, I mean, let me put some damping value here. Okay, so now you can see that it shows us the circular kind of behavior. So, I mean, if I increase it, so let me check what is the output. Still circular. So let me make it 5000. Still same. So that means system has reached into steady state. So you can, if you want to make your code more, accurate, then what you can do? So when you are calculating this FFT, you can, so instead of taking all the points, you can try to you can try to discard the initial point, and after that the points that you are getting after the initial transient is decaying down or died out, So the rest with rest of the point you can do the FFT analysis and so on. Okay, so this is how your phase space will look like. So now for this now our beta is 0. So now there let me show you another interesting type of plot. So which is image SC plot. So let me write down the code for this. So, so this is our figure 1, this is our figure 2. So let me call it figure 3. So let me write down the image SC. So basically, this is almost equivalent to 3D surface plot. So here, suppose in the x-axis I want the drive strength, in y-axis I want the frequency. So and in z-axis, maybe. So now what I want to do, I want to so this is the frequency domain response for one drive strength, and suppose I want to store them for the total range of this drive strength. So we can create an array initially. So TD array maybe an empty array, and here what you can do, so you can append P1 here. So or you can pre-allocate its length to increase the speed. So zeros, and what will be the length? So along row, so let us have the length of drive strength, and along column, so it will be of the length of P1, so n by 2 plus 1. So this and here we will update the TD array. So in TD array along ith row, so here row is the length of the drive strength. So for each drive strength, so that's why we have to write here I, and for ith row and along all the columns, we'll store the P1. So let me suppress the output and let me run it once. Okay, so let's just comment it now. And so since this is for one, drive strength, so it is showing this 1 into 5001. So let me increase it. So let me change the array from this, and let me write. I have 100 data points. So should I make it 1? Yes. And we have to suppress output somewhere. Is it maybe showing this one? And is there any other output which I need to suppress? Yeah. So now let us run this again. Okay, so this is for 10 data points, and you can see that so this is for drive. So for the initial drive strength, zero first element of the drive strength array, and this is the value of this uh, Fourier uh, Fourier transform or the PSD, and this is for second drive strength, and this is for third, and in this way for up to 11 drive strength we have stored the P1. So let us go to drive strength, and we can see that this is 11. There are 11 elements. So what is this output? Okay. So yeah. Now suppose I want to visualize this in a, I mean, so this is, I mean, this is right now plotting in a 2D plot. So here we have, so this for drive for the first element, for second, third, fourth, and so on. In this way it is increasing. Now suppose I want to visualize this whole thing in a 3D plot. So for that, what you have to do, so we have to use here the image SC, and here you have to write down the TD array. And then, I mean, so, and for let me run it and let me show you is the output. Okay. Okay, so this is the frequency axis, but it is inversed. So what we can do, we can make it from, I mean, so if you want to, I mean, it is always inverse. I mean, inverted in this images plot. So if you want to make it normal, so you have to write down this command. So set GCA y direction normal. Then, I mean, in 3D plot, you want to have the color bar. So, I mean, it always shows you from top. So, I mean, when you are doing a surface plot, so I mean, it shows you from various angles. But if you just want to show it from the top, so you have to write down in this way. And I mean, you can select maybe the y limit, can change from 0 to 4, and you can. So there are different kinds of color map. So I mean, you can look for it in the MATLAB documentation portal. Okay, so now we can see. So I mean, we have in, so this is how the system, I mean, this is equivalent to this. So how it is equivalent? So here this axis is a drive state. So I mean, in each, so for example, if you take a cross section along this, so this is for drive strength 0. So if we take a cross section, so this is for drive strength 6. And in the z direction, so the intensity, as we have learned earlier, so it represents the value. So here, I mean, around 1. So I mean, if you look at cross section, so as you can see, so these are the cross sections. So around 0, so we have this kind of cross section. So if I look at a cross section around this, and if I go around 10, so I mean, it will, in the cross, if we look at the cross section, then around 1 we have this red, dark red color. And I mean, you can see that its amplitude is large in this range, and that you can also verify from this cross section, from this 2D plot also. So I mean, you can plot all of this 2D data in a single 3D graph, so using this images function. And also, I mean, then you can change, so you can look for images C. And I mean, here you can go through the online documentation portal. So when it shows you this interesting kind of, it can so plot. So basically, I mean, you're projecting this on the, so I mean, in surface plot, I mean, you can make it rotate from different angle. So you are just projecting it on the, I mean, you are looking at from the top. So this is the images plot. And I mean, you can go to example, and you can look for different kind of example here. Okay, so this is how your system, so this is a simple harmonic oscillator system. Now, what will happen if I have some non-linearity in a system? So, I mean, let me make beta to be 5, and let me look at the system response. Okay, so now we can see that if we have some non-linearity, then there is a side, there is another peak which is emerging. So, and if you notice carefully, so that is at thrice, I mean, 3 times of this first peak. So I mean, so why it is at 3 times? Because you have cubic nonlinearity. So you have cubic nonlinearity present. So that is why, I mean, you have this cubic term. So I mean, if you increase the beta value, then you will have maybe different kind of response. So I mean, with in increasing beta value or with increasing type, you will have multiple peaks in your system. So let me show you with, make it 500. Okay, so and also you can see that here, so in this images plot, you can see that this faint line. So you can change the color map accordingly, or I mean, look at the. I mean, you can select the range of this number. So by which, I mean, you can make this graph look more prominent. Prominent, but the thing is that, so this is, I mean, you can look at how your system response is changing. So this is for drive strength 0. So I mean, so you have this uh, um, mm, uh, a graph similar to harmonic oscillator motion, but as you are increasing, so I mean, but now there is nonlinear in your system. So as you keep on increasing the drive strength, we can see that the shape of the, I mean, this phase space portrait is also changing. So let me uh, maybe increase the beta mode, so 5e4. So where there is much larger nonlinearity in a system now. Yes, you can see that the phase space is now looking complex, and there are also other orders of peak which are emerging. So, so let me just show you for a certain value. So let me show you for drive strength 1. And this is how a system look like. So let us increase the drive strength, and we can make it more. We can increase it more. So you can see that how your system, I mean, your corresponding phase space portrait is also changing. So here, what you can do. So now, let us try to make this nonlinearity 0. So if I make this nonlinearity 0, so this is a simple harmonic oscillator equation, and it will just give you, I mean, a circular kind of output. But as I introduce the nonlinearity, then I mean, you can look from the response that the phase everything has changed. So there are multiple peaks which are coming, and also there are multiple of initial response. So I mean, you can see, so and also the phase space portrait has also changed. So you can explore with various parameter values. So here you can also explore the effect of gamma. So maybe you can try to decrease it, and you can see that, so here the spectrum has also changed here again. So maybe you can make it 2, and you can try to look at the system response. Yeah, so with if I increase the gamma, so I mean, increasing the dissipation in the system. So if I increase the dissipation, then you can see that the system response is, I mean, changing. So you can explore the parameter dependence also. So how the parameter gamma will change your system, how the nonlinear term cannot change your system. So here also you can, I mean, introduce square nonlinearity, and I mean, look at the effect of square nonlinearity. So let me run it. Okay, so if I look at the response TD array, so NaN means it is going to infinity. So you have to then, I mean, this parameter value is not suitable. So you can try to lower the, what is the square nonlinearity, and I mean, in this way you can play with your parameter values. So maybe -2. Yeah. So yeah, so it is still harmonic kind of thing, and here you can see. So since we have introduced the square nonlinearity, so it is appearing at twice of the year fundamental thing. So that has a relevance. So I mean, if you look at, if you do the calculation in Fourier domain, So in that case you will see the connection, but that is an advanced. So you have to do this multiple time scale analysis and so on, which I will not go into. So that is a detailed topic. So, but in this way, you can explore the dependency on the parameter values. So let me make it cubic, and let me just run it. And also, so let us look at what is the value of fs. So let me take fs as an output also, and here also fs is output. So you're taking fs as an output. And let me look at what is fs. So this is 0.03. So what is fs? Fs is the sampling frequency. So so you can verify if this satisfy your Nyquist theorem or not. So by looking at, so this is the sample frequency, and you know what is the maximum frequency present in your system. So from that you can also verify it. So so here is the code. So with which you can play with the different kind of nonlinear system. So this is a for damping oscillator system. So you can introduce higher order nonlinearity here. So to the power 4, you can also solve a pendulum system with it. So you have to put a sine theta kind of term and so on. And you can put different kind of drive conditions. So instead of putting a direct drive, so you can add a drive to the, you can modulate the spring constant of the equation, so which generally known as Matthew equation. So you can try to explore these different kinds of things with, by taking different kind of oscillator system. Okay, so from the next lecture, so in the last two lectures, so what I will tell you, so I will show you how to solve stochastic differential equation. So when you solve this, ordinary differential equation. So there's this general kind of trend that you have this x, for example, first order equation x dot equal to fx. There can be other parameter also t. So or these are autonomous systems. So these a first order differential equation. Now suppose if your system, so there is what will happen if there is any random number or the noise term. So random number, for example, suppose they are present. So now you cannot use traditional differential equation method because this is not an analytic function. So since this is not an analytic function, so you cannot use the traditional RK2, RK4, Euler, and so on. So this we cannot use for solving stochastic differential equation. So and also the noise, if it is additive or multiplicative, depending on that, your system will respond differently. So in the last part of our lecture, so we will try to explore how we can solve this different uh, uh, this stochastic differential equation. So we will try to learn solving stochastic differential equation. So by the way, you can try to you can try to simulate this Matthew equation. So what is this Matthew equation? So you're modulating the spring constant. So the drive term. So till now what you are doing is m x dot plus gamma x dot plus beta x cube, and here we are adding the driving term additively. So this is why it is additive, because we are directly adding it to the equation. But so the drive you can also, with drive, so there will be omega square x. So you this omega square term you can modulate. So 1 plus f drive. So you can put this kind of drive also to your system. So now the equation will be like mx double dot plus omega square into 1 plus f drive x plus beta x cube equal to 0. So this type of equation where you are modulating the spring constant is generally known as Matthew equation. And this drive term, so I mean it can be so if this is a periodic function, so it can be a period of it can be a function of period t, and this and if t0 is I mean t0 is natural period, so corresponding to natural frequency. So if this t0 t is t0 by n, so that is known as parametric resonance. So parametric resonance case. And when this n matches with I mean so for n equal to 2, so when we have the drive frequency, so which is 1 by f drive, so which is 1 by n f0. So fd is basically 2 of f0 for n equal to 2. So if the drive frequency is twice of the natural frequency, in that case we generally observe Arnold. So in I mean nonlinear dynamics is known as Arnold tongue kind of instability. So you can try to look at it and you can try to simulate it in this system. So I mean you can corresponding to what the equation is given, you can change your model equation and you can explore I mean the I mean how your system responds with different kinds of with different parameter values.